Okay, here's the solutions to questions 6 and 7 in the Newton's laws practice problems. So what we have here is a rope holding up a rock on an inclined plane, and the inclined plane's at 30 degrees. And on the right you'll see I drew a coordinate system, and notice that I've placed the x-axis in the same direction as the slope of the plane. So let's first draw our free body diagram for the rock. So the first thing to note is I drew a coordinate system, I labeled it. I'm going to place the object as a circle at the origin of the coordinate system. Then I'm going to draw all the vectors. So the first vector is going to be the tension in the rope. So the tension in the rope is along the x direction, that's in the positive x direction. And there it is there. So that's our tension. Because the rock is on a surface, there's a normal force, and the normal force is perpendicular to the surface, so it's upwards. And finally, there's the weight, and the weight is downwards. Note that it's straight down, like that. Okay, so why don't we label all these. So this first one we said is the tension. This one up here is the normal force, and we have the weight pointing downwards. A couple of things I'm going to indicate here, and that's the x and the y components of the weight. So I'm going to draw this right angle triangle here, and also this angle in here, theta is actually 30 degrees. You can verify that via some geometry. Okay, so there is our free body diagram. So the first question, question number 6, is to determine the tension in the rope. So here I'm going to look at the sum of the x components of the forces. This rock is in static equilibrium, so the sum of the x components of the forces should be 0. Note that the normal force is just in the y direction, so it doesn't have an x component, but our tension force does have an x component, and so does our weight. And from Newton's second law, this is equal to mass times acceleration in the x direction, which is 0 because the rock is in static equilibrium. Okay, so note that, well, we can solve for Tx. And Tx, note that Tx doesn't have a y component, so its magnitude is just going to be the x component. And from the equation above, this is just equal to minus the x component of the weight. Now the x component of the weight is this side of the triangle down here. And the x component of the weight is negative because it's in the negative x direction. The weight points in the negative y and the negative x direction. So So we have the minus sign and then another minus sign because the weight has a negative x component, and it's related to the magnitude of the weight, which is the mass times the acceleration due to gravity. And because we're only interested in the x component, we have to multiply by sine of our angle theta, which is 30 degrees. There. So, solving for t, we just plug in some of the values. Note that the mass is, well, first of all, note that the two negative signs cancel. The mass of the rock is 10 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And sine of 30 is a half. So this is equal to 49 newtons. Okay, and, well, technically this is to 1 sig fig here, so we round this to 1 sig fig, which is 50 newtons. Okay, So question 7, suppose the rope breaks. What would be the rock's acceleration down the incline? Well, so if the rope breaks, then the tension force goes away. And the only force which has an x component is the weight. And, well, at least the x component of the weight. So the x component of the weight, we said, was minus mg sine 30 degrees. So now we just, and this is the force, right? This is going to give us a force. So we calculated this to be minus 49 newtons. And so, remember Newton's second law, force is equal to mass times acceleration. So this is the acceleration in the x direction. So, our acceleration in the x direction, that's a big X, why don't I make that a little bit clearer. We're solving for x, it's just negative 49 newtons divided by our mass, which is 10 kilograms. So we get negative 4.9 meters per second squared. And again, this is to 1 sig fig, so this is minus 5 meters per second squared. And there's the acceleration down the incline.